The Road Safety Act states that all passengers in a car should wear their safety belts. Why do you think this is? Do you think that what you have learned so far about forces and bodies in motion can help you answer this question? Imagine what would happen if you weren't wearing a safety belt in this accident. It is quite clear that if you don't wear a safety belt, you stand a good chance of being seriously injured when a car stops suddenly. But why does the force that stops the car not also stop the passenger? Let's consider Newton's first law again. Newton's first law of motion tells us that a body remains at rest or moves with constant velocity in a straight line unless a resultant force acts on it. When the car hits the barrier exerts a force on the car, and the car exerts a force on the barrier. The resultant force causes the car to stop suddenly. Notice that the interacting bodies here are the car and the barrier. There is no resultant force acting on the passenger. Therefore, according to Newton's first law, the passenger keeps moving. He continues moving forward at the same speed and in the same direction until a resultant force acts on him. Unfortunately, this normally happens when the passenger's head collides with the windscreen. This impact can be fatal, or it can cause very serious head injuries. To make sure that you truly understand this application of Newton's first law, let's look at another example. I've placed a coin onto a stiff piece of cardboard. Look at what happens when I flick the cardboard horizontally. Do you see that the coin remains in the same place as the cardboard flies away? Can you explain how this happens? The coin remains at rest because there is no resultant force acting on it. The cardboard, however, flies away when I flick it. The resultant force was applied only to the cardboard, not to the coin. So the inertia, in other words, that property of the coin that resists a change in its motion, kept it stationary, that is, at rest. Now, in our previous lessons, we've established that all bodies in motion also have a property called momentum. In addition, we've discovered that a body's momentum will only change when a resultant force acts on it. This is a confirmation of Newton's law. In addition, we now know that a body's change in momentum is described by using the quantitative term impulse. In today's lesson, I would like us to investigate the link between the magnitude and direction of the resultant force and the rate of change in momentum. By the end of this lesson, you should be able to explain the relationship between the rate of change of momentum and the resultant force, and apply Newton's second law of motion. I would like us to start our investigation by looking at an interesting puzzle. Let's see if Dineo and her friends can help us with it.
Hi Nelly, we've got Tandy standing by with 2 eggs needed for this part of the puzzle.
Tandy has 2 raw eggs in her hands. First, she's going to drop one of the eggs from a height of 1,5 meters onto a tabletop.
Clearly, the resultant force that the table exerted on the egg quickly changed the egg's momentum to 0.
Correct, Dineo, but what do you think will happen if you guys try the same thing with a linen sheet held in place instead of the table? Why don't you give it a go? Once again, we get Tandy to drop a raw egg from a height of 1,5 meters.
Look, Nelly, the egg doesn't break this time. The sheet saved it.
Tandy, won't you drop that same egg onto the tabletop just so that we know you're not cheating and using a boiled egg? And there you go. It breaks. What saves the egg? The egg traveled at exactly the same velocity when it hit the tabletop as it did when it hit the sheet, because it has fallen from exactly the same height in both cases. Therefore, the change in momentum is the same in both cases. So what is it that is different? Do you agree that we would have to say that the resultant force exerted by the sheet on the egg was somehow less than that of the tabletop? But why? Let's look at the demonstration again, but this time in super slow motion. On replay, you should be able to see that when the egg smashed into the tabletop, it came to a stop quicker than it did when it fell onto the sheet. In other words, the contact time between the table and the egg is shorter than the contact time between the egg and the sheet. Now look at the equation we used to describe impulse again. Remember, impulse is the same as change in momentum. If the change in momentum or impulse is the same in both instances, but the contact time when the egg hit the sheet is greater, do you see that you need to have a smaller force to get the same answer than you would need if the time was shorter? Although the change in momentum is the same, the time taken for this change in momentum is longer. So the rate of change of momentum, delta P, over the time taken, is greater when the egg hits the tabletop than when it hits the sheet. So we can conclude that given a longer time to stop, the rate of change of momentum of an object is reduced, and so is the resultant force. To summarize, we can say that resultant force depends on the rate of change of momentum. Now, Sir Isaac Newton made similar observations during the experiments he was doing in the 17th century. His results are stated in his second law of motion. The resultant force is directly proportional to the rate of change of momentum, and it acts in the same direction as the change in momentum. Notice that he also makes a statement about the direction of the resultant force in his law. This is of course correct because we know that force is a vector quantity. To understand how he got to his conclusion about the direction of the resultant force, we can do a very simple calculation. If the egg in our example has a mass of 30 grams and travels with a velocity of 1 meter per second, we can use the equation P equals mu to calculate the initial velocity of the egg as 0.03 kilogram meters per second. Change in momentum is calculated by subtracting the initial velocity from the final velocity, in this case 0. So the change in momentum is negative 0.03 kilograms meters per second. Now in science, the general rule when defining vector signs is that the direction of initial motion, in our example that is downwards, is positive, and the direction opposite to the initial direction of motion is negative. In our example, this is the upward direction. So if the resultant force that stops the egg comes from the table, which is exerting an upward force, then the direction of the resultant force is negative according to the convention. Look at our calculation again. Do you see that our answer is negative 0.03 kilogram meters per second? So we can say that the resultant force acts in the same direction as the change in momentum. Now let's analyze Newton's second law mathematically to see what it is really saying. It says that the resultant force is equal to the change in momentum divided by the time taken for the momentum to change. We know that change in momentum is equal to mass times the final velocity minus mass times the initial velocity divided by the time taken, which is the same as saying mass multiplied by the change in velocity. But you should recall from your study of motion that the rate of change of velocity is called acceleration. So we can say that the resultant force is equal to the mass of the body times its acceleration, and this does make good sense. We already know that when a resultant force acts on a body, it causes it to either increase its velocity or to decrease its velocity. When the velocity of a body changes, we say that it is accelerating. The resultant force accelerates the body in the same direction as the resultant force. But how is the acceleration of the body related to the resultant force? To answer this question, we rearrange the relationship, making the acceleration A the subject of the formula. This tells us that the acceleration is directly proportional to the resultant force, and it is in the same direction as the force. And the acceleration is inversely proportional to the mass of the body. Newton's second law of motion is often stated in this way, in terms of the acceleration of the body and its relationship to the resultant force and the mass of the body. Why don't we see if we can confirm this relationship in the lab?
Hey there guys, now look here, I've got a little car and a friction compensated track. Now what that means is that our track has got so small frictional force that we can ignore it during our calculations. And the track has been designed in such a way that our car can run down it at constant speed. We can check this by attaching a ticker tape to the trolley and letting it run on the track. Do you see that the displacement of the trolley over equal time intervals is the same? This tells us that the car travels at constant velocity. Now I'm going to attach this weight onto the car using the slide string. Now the slide string is designed in such a way that it doesn't stretch when I attach a weight to it. Now, the weight hangs over this frictionless pulley and it pulls the trolley along the track. The trolley accelerates when the weight is attached to it. We can see this by analyzing the ticker tape. Now, our analysis will also tell us about the rate of acceleration. The displacement increases in equal time intervals. We can see that there's a constant rate of increase in displacement in each of these time intervals. So the acceleration of the car is uniform. Now we're going to use this apparatus to verify Newton's second law of motion. Firstly, we need to measure the acceleration of the trolley as we change the resultant force applied. The independent variable is the resultant force. Acceleration depends on the force, so acceleration is the dependent variable. To make this a fair test, we must make sure that our system mass is constant. Let's begin by loading up the mass to achieve our maximum resultant force. There you go. Now let's release the car, but remember, be careful not to let the weight hit the floor before the car completes its run. Go for it. Now we must analyze this tape and label the force we used as 2,5 Newton. Next, we're going to change the resultant force and let the car run again 4 times. Now what I'm going to do in each run, I'm going to take one mesh piece off the weight, put it onto the car. Now that reduces the resultant force, but it makes sure that the mass of the system is constant, and it ensures that this is a fair test. Well, Nelly, I think we've got enough data for you to analyze.
Thanks, Aaron. Let's draw a graph using the data Aaron collected in the lab. When the results are plotted on a graph, we can see that as the resultant force increased, so did the acceleration. In other words, the acceleration is directly proportional to the resultant force and in the same direction as this force. Do you think we can use the same setup of apparatus to verify the relationship between the acceleration and mass of the trolley? Think about it. If we keep the resultant force constant and change the mass of the trolley, we should be able to do it. So we begin by accelerating the trolley using the force which we have on it now. Collect the tape and analyze it. Then we take off one of the mass pieces and repeat the trolley run with the same resultant force applied. If we graph these results with mass as the independent variable and acceleration as the dependent variable, the graph shows us that as the mass increases, the acceleration decreases. It seems to have the shape of a hyperbola. But to check that the results truly give us an inverse relationship, we must plot a graph of acceleration as the dependent variable and the inverse of mass, 1 over mass, as the independent variable. This will be your task for today. Take down this table of results. Complete the column where you calculate the value of the inverse of mass, 1 over the mass, and plot a graph of acceleration against 1 over mass. Remember to state your conclusion for this part of the experiment. Physics is in the business of making sense out of everyday phenomena. Predicting how things move is essential to our technological and social world. Join me next time when we discuss what happens when things bump into each other.